4.7 Lesson 1, Graphs and Derivatives of Implicit Relations. Our objectives are 1, you'll be able to identify implicit relations, and 2, you'll be able to find derivatives of implicit relations by using implicit differentiation. To understand what an implicit relation is, we will begin by looking at functions that we've seen again and again in our course. Those were explicit relations. So what is an explicit relation? It's an equation that defines y as a function of x. So for example, y is equal to x squared, or y is equal to 2x plus 5, or y is equal to 5x squared minus 1. These are all examples of explicit relations. Even y is equal to sine x, y is equal to arc cosine of x. These are all examples of explicit relations because they define y as a function of x. What's an example of an implicit relation? You don't have y isolated in an implicit relation. So for example, you could have x squared plus y squared is equal to 25. This is an implicit relation because we do not have y isolated. Here's another implicit relation. We have x plus x squared times y cubed plus y is equal to sine of 2x. So the question is, if you have an implicit relation, such as the two that we just wrote, and you want to find dy dx, the derivative of y with respect to x, how would you do it? And there is a procedure called implicit differentiation for finding dy dx for implicit relations, and that's what we want to learn today. We will begin by considering an implicit relation such as the one that we wrote first. There are some implicit relations for which you can isolate y and rewrite it as either one or perhaps more than one explicit relation. So for example, here I can isolate for y, and y would be either the positive or the negative square root of an expression. So I can rewrite this implicit relation as two explicit relations. And for each explicit relation, I can figure out y prime. However, there may be other implicit relations for which it may not be so easy to isolate y, or maybe even it's not possible. And in that case, you would have to use what we're going to learn today, implicit differentiation. As a final note, you of course have already learned how to find derivatives of all of these explicit relations that I wrote earlier as examples for explicit relations. Our focus today is on finding derivatives of implicit relations by using implicit differentiation. In the equation x squared plus y squared is equal to 25, which is an implicit relation because we do not have y isolated, we want to solve for y. In other words, we want to rewrite the implicit relation as two explicit relations. In the first case, solving for y by taking the positive square root and then finding y prime using the chain rule. And in the second case, solving for y by taking the negative square root and then finding y prime by using the chain rule. So we'll go ahead and do that now. So we have x squared plus y squared is equal to 25. And I can begin by subtracting x squared from both sides of the equation. And in the first case, for number 1, I can take the positive square root to get y by itself. But of course, this is only half of the relation that is implied by the equation x squared plus y squared is equal to 25. And if you graph it, you'll get a circle centered at the origin with radius of 5 units. And this explicit relation will give you just the top half of the circle. And for number 2, you can solve for y by taking the negative square root, and then we would like to find y prime by using the chain rule. So if you solve for y by taking the negative square root, and then you graph this explicit relation, you'll get the bottom half of the circle. And of course, the two halves of the circle together will give you the full circle that is given by the implicit relation. So the implicit relation can be represented as two separate explicit relations. And these two explicit relations taken together will give you the same circle given by the implicit relation. So now, for each of the explicit relations, we can find y prime. And we can do that by using the chain rule. So in the first case, we can write the square root of 25 minus x squared as 25 minus x squared to the 1/2 power. And in the second case, we can write negative 1 times 25 minus x squared to the 1/2 power. So this is, of course, just y. And we're trying to find y prime. So to find y prime, you have to use the chain rule because you have an inside function and an outside function. So we begin by using the power rule. Subtract 1 from 1/2, I get negative 1/2. And then multiply by the derivative of the inside function. So I will have the derivative with respect to x of 25 minus x squared, which is, of course, negative 2x. So I get y prime is equal to negative 2x times 1/2. And this power, because it has a negative exponent, I can rewrite it to be in the denominator with a positive exponent of 1/2, which can then be written as the square root of 25 minus x squared. And of course, you can see that the 2 here will cancel with the 2 here, leaving me with negative x over the square root of 25 minus x squared. So that is y prime for the explicit relation given by number 1. If I want to find y prime for the explicit relation given by number 2, I will have y prime is equal to, again, I will have to use the chain rule. I have an inside function and an outside function. So I also have a factor of negative 1 here. So I have negative 1 times 1/2 times 25 minus x squared to the negative 1/2 power. And now I must multiply by the derivative of the inside function using the chain rule. The derivative of the inside function is negative 2x, so I have y prime is equal to, I have this negative 1/2, and then I have negative 2x, the derivative of the inside function, times negative 1/2. And of course, this power here with the negative exponent can be taken to the denominator, and it will have a positive exponent of 1/2, which can be written as square root. So when you simplify here, you can see that the 2 and the 2 will cancel, and negative times negative is positive, so that leaves you with just x over the square root of 25 minus x squared. So we have done the following. We took our implicit relation, wrote it as two explicit relations, and for each one we found y prime by using the chain rule. We'd like to make one observation before moving on to doing the same problem by using something called implicit differentiation, which will give us the same derivative, but you will find it to be easier. And although it was not necessary in this particular problem, it will be easier. And in other problems where you cannot isolate y from the explicit relation, implicit differentiation would be the only way that you would know how to find the derivative. But before we do that, let's take a look at if we can simplify what we have here. So in the first case with number 1, I have y prime, and I have negative x in the numerator, and in the denominator I have the square root of 25 minus x squared. And of course, if you look at what we have for number 1, the square root of 25 minus x squared is y. So I can replace that with y, and for number 1, I can write y prime is equal to negative x over y. And let's see what we can do for number 2. For number 2, we have y prime is equal to x over, and of course you have the square root of 25 minus x squared. And if you look at number 2 here, here's the square root of 25 minus x squared, and if you multiply both sides of this explicit relation by negative 1, that quantity, that radical expression, would be equal to negative y. So you have x divided by negative y, so we get y prime is equal to x divided by negative y. And of course, these are both the same. They're both negative x over y. So we get the same derivative for both the top half and the bottom half of our circle. But it was a bit of work. Let's see if we can do it a different way using something called implicit differentiation. We have the same problem that we just did. So when we find y prime, we should get the same y prime that we just found. But we're going to do this now using implicit differentiation. And you will find this to be easier than what we just did, and for other problems necessary to find y prime, because you would not be able to isolate for y explicitly for other problems that you might be doing. So guidelines for implicit differentiation. We're using the chain rule when we use implicit differentiation. And the assumption that we're making is that y is some differentiable function of x. Whether we know what it is or whether we don't know what it is, we make the assumption that y is some differentiable function of x. So when you look at y squared, you see this as a composition of two functions, where the inside function is y, whether known or unknown. We assume that y is some differentiable function of x, and the outside function in this example would be the squaring function. And we can differentiate both sides of our equation with respect to x, and when we differentiate the term y squared, we would have to use the chain rule. So look at the steps here. Guidelines for implicit differentiation. Differentiate both sides of the equation with respect to x. Collect all terms involving dy dx, which is of course y prime, on the left side of the equation, and move all other terms to the right side of the equation. Factor dy dx out of the left side of the equation and solve for dy dx. So we begin with step 1, differentiate both sides of the equation with respect to x. So we have the derivative with respect to x of x squared plus y squared is equal to the derivative with respect to x of 25. So the next step would be on the left side of the equation we have a sum. So we're going to write the derivative with respect to x of the first term plus the derivative with respect to x of the second term, which is a composition of two functions. And on the right side we have the derivative with respect to x of the constant 25. So the easy things to do in this next step are the following. We know this derivative will be 0 because the derivative of a constant is 0. So we can just write that has to be equal to 0. We also know that this derivative, you're just differentiating with respect to x. So you just use the power rule and you get 2x. So how do we deal with this one here? Again, as I said earlier, you see y squared as a composition of two functions, where the inside function is y and the outside function is squaring. So you use the chain rule. So the derivative of the outside function is found using the power rule. So you bring the 2 to the front, subtract 1 from 2, you get 1. And then you have to multiply by the derivative with respect to x of the inside function y. That is the chain rule. And what is this? This is what we're looking for. It is dy dx, or y prime. Let's write dy dx, and you'll see why this is a good habit to have when we look at related rates in our next section. So we have 2y times dy dx is equal to 0. So what have we done? We differentiated both sides of the equation with respect to x. Step 2, collect all terms involving dy dx on the left side of the equation, or you can say on one side of the equation, and move all other terms to the other side of the equation. So I have this term, which has dy dx. So I will subtract 2x from both sides of the equation. So step 2, I have 2y times dy dx is equal to 0 minus 2x, which is negative 2x. Step 3, factor dy dx out of the left side of the equation. Well, I only have one term, so there's nothing for me to do for step 3 here. And then finally, step 4, solve for dy dx. So 3 is nothing to do, and 4, we're going to solve for dy dx by dividing both sides of the equation by 2y. So that gives us negative 2x divided by 2y. The 2 and the 2 will cancel, and of course, what do we get? We get dy dx is negative x over y. So we verified using implicit differentiation that y prime, or dy dx, is the same as what we found using in which we rewrote the implicit relation as two explicit relations and then found derivatives of each one using the chain rule. So we get the same result doing it this way. But again, as I said, in this problem, you could have done it differently. In other problems, you would have to do it this way. And what information does this tell us? Slopes of tangent lines to the graph of x squared plus y squared is equal to 25 at various points on the circle given by this equation. So if you want to know, for example, consider a particular point on the graph of x squared plus y squared is equal to 25. So x squared plus y squared is equal to 25 gives us the red circle centered at the origin with the radius of 5. And dy dx would tell us the slope of the tangent line to the circle at a particular point on the circle. So for example, if you look at the point 4, 3, it is a point that is on the circle. How do I know that? Because if you square 4, you get 16, and if you square 3, you get 9, and 16 plus 9 is 25. So we know that 4 squared plus 3 squared will give us 25, so the point 4, 3 is on our circle. What is the slope of the tangent line to the circle at the point 4, 3? If you want to know that, you are just going to evaluate dy dx, and here's the notation that you use. Evaluate dy dx when x is equal to 4 and when y is equal to 3. So this is how you write the notation for using the derivative and evaluating it at a particular point on our graph with coordinates 4, 3. So dy dx evaluated at x is equal to 4 and y is equal to 3 is, just substitute 4 for x and 3 for y in the equation for dy dx. And we're going to get, that would be negative 4 divided by 3. So the slope of the tangent line to the circle at this particular point is given by dy dx evaluated at the point, and we now know that the slope of the tangent line is negative 4/3. And using that, I can sketch my tangent line to the circle at the point 4, 3. So the derivative gives us the same information that it's given us all along, slopes of tangent lines to the graph. And of course, before we did implicit differentiation, we rewrote our equation as y is equal to the positive square root of 25 minus x squared, giving us the top half of the circle, and y is equal to the negative square root of 25 minus x squared, giving us the bottom half of the circle. And we found y prime. And of course, you can also just go ahead and evaluate y prime. If you done it that way, you would have gotten the same derivative. So you get the same slope, same information. Let's take a look at another example. We want to find dy dx for this implicit relation, x plus x squared y cubed plus y is equal to sine of 2x. And as you can see, the difference between this one and the previous one is if you were to try solving for y, you may not even be able to do it. So how do we go ahead and find dy dx if we can't solve for y? By using implicit differentiation. So we follow these steps. We begin by differentiating both sides of the equation with respect to x. We will assume that y is some differentiable function of x. So when you have y cubed, you see that as a composition of two functions, where the inside function is y and the outside function is cube. So we begin with step 1. So we will differentiate both sides of the equation with respect to x. We differentiate the left side of the equation. And we differentiate the right side of the equation with respect to x. So on the left side of the equation, you have 3 terms. So you're going to write the following. The derivative with respect to x of the first term x plus the derivative with respect to x of the second term x squared y cubed, which is a product. So when we find this derivative, we'll have to use the product rule, plus the derivative with respect to x of the third term y. And on the right side, we have the derivative with respect to x of sine of 2x. So now some of these are really easy to do. Like here, you just find the derivative of x with respect to x, which is 1. Here you have to use the product rule because you have a product. You have x squared times y cubed. So you're going to write the derivative of the first function times the second function plus the first function times the derivative of the second. And notice that you're taking the derivative with respect to x of y cubed. And then you're going to take care of this. Right now I'm just going to write it as I have it. It is going to give us dy dx. And on the right side of the equation, you would have to use the chain rule because you have an inside function 2x and an outside function sine. You're taking the derivative with respect to x of sine of 2x. So using the chain rule, you have the derivative of sine, which is cosine, and then multiply that by the derivative of 2x with respect to x, which is 2, giving you 2 times cosine of 2x. So now we'll go ahead and complete the steps here. So I have 1 plus, what is this derivative with respect to x? It is 2x. So I write plus 2x y cubed plus, what do we do here? Well, I just write the x squared, and then I have to take the derivative of y cubed with respect to x. Again, you see y as your inside function. The outside function is the power function raising to the third. So you use the power rule, you get 3y squared, and then you multiply by the derivative with respect to x of the inside function y, using the chain rule. So now you have plus this will give us the derivative with respect to x of y, which is dy dx. And that's equal to 2 times cosine of 2x. So as I said earlier, this is dy dx, and this is also dy dx. And that's what we're looking for. So I will go ahead and just replace each of those with dy dx. So we have done step 1 from the guidelines. We have differentiated both sides of the equation with respect to x. What is step 2? Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. So I have 2 terms that have dy dx in them. So that's one term, and this is another term. The other terms do not have dy dx, so I will move them to the right side of the equation. And then after I do that, I will do step 3. Factor dy dx out of the left side of the equation, and then finally solve for dy dx. I will show step 2 in blue just to sort of distinguish it from the other work. And all I have to do is subtract 1 from both sides of the equation and subtract 2xy cubed from both sides of the equation. And when I do that on the left side of the equation, I'll have x squared times 3y squared. I can write the 3 out front. So 3x squared y squared dy dx plus dy dx. And that's equal to, I can write 2 cosine 2x, and I can subtract these 2 terms from both sides of the equation to get me minus 2xy cubed minus 1. The next step is to factor out dy dx from the 2 terms on the left side of the equation. So when I factor out dy dx from the first term, what am I left with? And I'll show this in green. So I will write dy dx, and when I factor it out from the first term, I will be left with 3x squared y squared. And when I factor it out from the second term, I'll be left with a factor of 1. So I have plus 1. And on the right side of the equation, I have 2 cosine 2x minus 2xy cubed minus 1. And I will now solve for dy dx. That is my final step. And how do I solve for dy dx? In step 4, all you have to do is isolate dy dx. Get it by itself. You can see that dy dx is being multiplied by the factor in the green brackets. So I will divide both sides of the equation from step 3 by the factor in the green brackets to get dy dx by itself. So dy dx is equal to, when I divide the left side by the green bracket factor, I will isolate dy dx, so I have to do the same thing on the right side. So I already have 2 cosine 2x minus 2xy cubed minus 1 on the right side. And now I will divide that by 3x squared y squared plus 1 from the left side of the equation. And that is my final answer. So our next example is this. Find dy dx for sine of x times y is equal to x squared y. And again, we will recognize that this is an implicit relation, and you may not even be able to solve for y explicitly. It doesn't seem like we can. We're going to find dy dx by using implicit differentiation. We begin with step 1, differentiate both sides of the equation with respect to x. So we're going to write the derivative with respect to x of the left side of the equation is equal to the derivative with respect to x of the right side of the equation. You will recognize that on the right side of the equation you have a product, so you have to use the product rule. And on the left side of the equation you actually have a composition. You have sine, which is your outside function, and your inside function is x times y. So your inside function is a product. So let's go ahead and do this. So beginning with the left side of the equation, you begin with the chain rule. Take the derivative of the outside function with respect to x. The derivative of sine is cosine. So you have cosine evaluated at the inside function xy, and then multiply that by the derivative with respect to x of the inside function xy. This is what the chain rule tells us to do. And we're going to go step by step. And on the right side of the equation we have a product. So to find the derivative with respect to x of x squared y, we have to use the product rule. So we have the derivative of the first function times the second function plus the first function times the derivative with respect to x of the second function. So now our next step would be to go ahead and find this derivative here. We will find this derivative here, and this is of course dy dx. So to find this derivative we have to use the product rule. To find the derivative of x squared with respect to x, that's just 2x, so that's really easy. And this derivative, the derivative of y with respect to x, is dy dx. So all we have to do is use the product rule here, and the other two are pretty straightforward. So now we have cosine of xy. One thing to remember is cosine of xy is being multiplied by this derivative. So when you use the product rule, you will get two terms. Make sure you multiply both terms by cosine xy. So we will have the derivative of the first function times the second. So we have the derivative with respect to x of x times the second plus the first function times the derivative with respect to x of the second. So that's the product rule. And that's equal to, on the right side of the equation, what is this? As we said earlier, that is 2x. So we have 2xy plus x squared. And what is this? This is dy dx. That's what we're looking for, dy dx. And what is this? The derivative of y with respect to x, that is dy dx, what we're looking for. So we will replace that with dy dx. And what is this derivative? The derivative of x with respect to x is 1. So we just have 1 times y, or just y. So now we have completed step 1 from the guidelines. Differentiate both sides of the equation with respect to x. Step 2 is to collect all terms involving dy dx on one side of the equation and move all other terms to the other side of the equation. So you will look at what we have here and you will look to see where we have dy dx. Well, we have dy dx here, and we also have dy dx here. But remember, cosine of xy has to multiply both of these terms. So before you can try to get dy dx on one side of the equation, you need to multiply both of these terms by cosine xy. So that will give you y times cosine xy. So I will write y times cosine xy plus x times cosine xy times dy dx. And on the right side of the equation, I have 2xy plus x squared dy dx. And now I can see that these are the two terms that have dy dx in them. And step 2 says collect all terms involving dy dx on one side of the equation and move all other terms to the other side of the equation. So we'll do that, and then we will factor dy dx out of the two terms on the left side of the equation, and finally solve for dy dx. So I can just move this term to the left side of the equation by subtracting it from both sides of the equation, and I can move this term to the right side of the equation by subtracting it from both sides of the equation. So that would give me, on the left side of the equation, I will have x times cosine xy dy dx minus x squared dy dx, and that would be equal to, on the right side of the equation, I will have 2xy minus y times cosine of xy. Step 3 is for us to factor out dy dx from each term on the left side of the equation, and I will show that in green. So when I factor out dy dx from the first term, I'll be left with x times cosine xy. When I factor out dy dx from the second term, I'll be left with minus x squared. So I will have dy dx, and I'm left with x times cosine xy from the first term and minus x squared from the second term. And that's equal to, on the right side of the equation, 2xy minus y times cosine xy. And my last step is to solve for dy dx. So to complete step 4, we just need to divide both sides of the equation by the factor multiplying dy dx on the left side of the equation. So we will have dy dx isolated, and that would be equal to what we have on the right side, 2xy minus y times cosine of xy divided by x times cosine of xy minus x squared. And that is the final answer. In today's lesson, we understood the difference between explicit relations and implicit relations, and we learned a procedure called implicit differentiation that allows us to find dy dx for relations that are defined implicitly, such as x squared plus y squared is equal to 25, and we did 2 other examples after that. And in lesson 2, we'll look at 2 additional examples for using implicit differentiation to find derivatives of implicit relations.